Good afternoon. Our speaker today is Andrei Manolescu. Andrei did his PhD at the Institute of Atomic Physics in Bucharest, and then he spent some years later in different places, in the University of Regensburg, at Bilkent University, at Max Planck Institute in Stuttgart, and ICTP in Trieste. And since 2008, he is professor at Reykjavik University. He has been visiting IFISC for almost 3 weeks now. During the course of a sabbatical period, he has, and we have been working in common projects and extending an ongoing collaboration. Andrei is a condensed matter physicist, theorist, a well-known condensed matter physicist, but he also has experience in the field of genetics. And actually, last week he gave a talk on genetics that maybe some of you attended. And today he is going to tell us about his other main topic on condensed matter, specifically nanowires, electronic states in core shell nanowires.
Thank you. I assume everybody knows what nanowires are, and I'm not going to insist on that. I will start with 2 pictures showing nanowires grown by 2 different methods and by 2 different groups. In the top figure, you can see an array of nanowires. It's actually 2 arrays, 2 figures, built in Germany, in Jülich, in the group of Thomas Scheppers. And these nanowires are grown bottom-up, so they grow the nanowire starting with a little droplet, and then they deposit atoms, and they grow, let's say, vertically. The second picture shows nanowires fabricated with a so-called top-down method, which consists of taking a material block and etching. So the result is this array of nanowires, which can be as long as 20 microns. And these are produced by Alters Babarsson in University of Reykjavik in our group. Now, in particular, core shell nanowires are more or less like this pencil. So you have a shell, in this case a plastic, and another material inside. In this example, there is a gallium arsenic core, and surrounding that core, it's an indium arsenic layer or shell. And the most interesting case is when the shell, or at least for me, when the shell is conductive and the core is insulating, because then you have transport along the tube. And of course, tubular structures can be produced in many ways. In some cases, one can even dissolve the core, and you are left with vacuum inside. And of course, we know about carbon nanotubes, which are much smaller. The typical size of a core shell nanowire is like 30, 50 to 100 nanometers diameter, and the length can be microns, 10 microns, 20 microns. Now, in the Thomas Scheppers group, they attach, in fact, they grow arrays, and then they can pick some wires, put them on the substrate, and attach contacts, so they can observe the behavior of individuals nanowires. And then by attaching these gates or contacts, they can actually probe the conductance only of a segment of the nanowire. And observe the shape. The shape tends to be with a hexagonal cross-section. So I will come back at the cross-section a little bit later. So I would like to talk about three types of localization. So now from the point of view of the electronic transport, one localization is radial localization. The electrons are on a tube. Then I will also talk about a sort of lateral localization which can be produced by external magnetic fields. And then I will talk about the localization in the corners. Now, the first example or the first effect of the localization in the radial direction is the observation of Aharonov-Bohm oscillations or flux periodic oscillations in the presence of a magnetic field along the nanowire. So in these experiments, you observe the oscillations of the conductance versus magnetic field. In addition to the small oscillations which are attributed to the Aharonov-Bohm effect, then one can see also some modulations. The first simple, please.
Modulation is due to weak localization effects?
It can be for several reasons. According to the experimentalist in the original paper, it is because universal fluctuations in the, because of some sort of impurities. According to our calculations that I will show, it can be also because of the spin. But that can also be a source.
What is the difference between the two curves? Is the symplectic
At least not in this.
with black and purple?
Tends to be, or at least I'm not aware of such an interpretation of this data. But in other cases, they claim they see weak localization.
But the difference between these two data is just which parameter do you change?
The voltage,
What is voltage?
the gate voltage. But we can look at that. Now, the first simple idea is the motion of an electron on a circular trajectory. So if we have a motion of an electron on a ring, we know that the energy spectrum consists of, at zero magnetic field, depends on an integer number to the square, which is the angular momentum. If we put a magnetic field, then we have a shift corresponding to the ratio of the magnetic flux to the flux quanta. So if you look at the energy spectra versus magnetic field, you have this periodic structure. And now, of course, the Aharonov-Bohm effect has a long history and many other interpretations. Some people do not accept that in this case the periodicity gives you the Aharonov-Bohm effect. They consider Aharonov-Bohm effect an interference effect of wave functions, but these are other details. But this is the origin of the flux periodic oscillation of the conductance. Now, if the spin is included, then we have to add a term which is linear in magnetic field, and then the periodicity is no longer valid. So depending on how strong is the G factor, the periodicity may be observed or possibly distorted. Now, the simplest model that we use for these nanowires is a cylinder with zero thickness and a finite or possibly an infinite length. So then we have angular momentum states, which describe the orbital degree of freedom. And then we have the typical sinus wave functions corresponding to finite length, finite and boundary conditions, vanishing boundary conditions at the two sides, and the spin term. In order to do transport calculations, we also need to attach the leads. And in a first attempt, we simply attach the leads and consider a very weak coupling between the leads and the nanowire. So a nanowire of finite length with some sort of contacts, weakly coupled, and we assume a kind of kernel of two overlap wave functions, and then we proceed with the standard formalism of ballistic transport, which I do not want to explain. It's basically Green functions, and we calculate the transfer matrix and then the conductivity. And indeed, we obtain the Aharonov-Bohm or flux periodic oscillations with our modulation. We also try to observe the effects of possible spin orbit, but this is another subject that I do not want to expand. And according to our calculations, the modulation appears because of the spin, and if we look at, because now the magnetic field is along the wire, so we can understand the spin effect as a splitting of the energy bands or energy states corresponding to the longitudinal motion. So if you have the ordinary states in a finite well, which corresponds to the length, then with the magnetic field, they would split and they would intersect. Now, if we look at the energy spectrum that we obtained for the finite length nanowire, it's complicated versus magnetic field or versus the magnetic flux. But you see traces of the bands corresponding to various longitudinal modes. And then if you look at a fixed chemical potential, Fermi energy, you see density of states effects, which is how we explain the modulation. And again, there might be possible reasons. This is the one possibility. Now, I would like to move to the second type of localization, which can be created in the presence of magnetic fields, and it is I would say less, or as much as you can call the radial localization trivial, less trivial than the radial case. If we have a magnetic field which is perpendicular to the nanowire, use this. This is the magnetic field. Then we know very well that the electrons are going to rotate due to the Lorentz force. So if you have a magnetic field perpendicular to a plane, if the electrons are situated in the plane, then they will rotate. But the force, the Lorentz force, is determined by the magnetic field component perpendicular to the plane. What we have in this case is a magnetic field uniform in space, but the surface bends. So what you have to look at to understand the motion is the magnetic field in the radial direction, because this is what is perpendicular to the surface. And if you look, what is the radial component of the magnetic field in this place, in this point, and what is the radial component of the magnetic field in this point, you observe a change of sign. In other words, on this surface, in the presence of the magnetic field, the electrons will experience a non-uniform magnetic field. The spin will always respond to the total magnetic field. But if we do not think about the spin, but only about the orbital motion will actually follow the magnetic field corresponding to the radial direction, to the perpendicular component. Now, if the magnetic field is non-uniform, so now it doesn't have to be on the cylinder. So suppose we have a magnetic field up and down. In between these regions, there is a place where the magnetic field is zero. So if an electron comes with a velocity which is such that the Lorentz force bends the trajectory towards the zero magnetic field line, then when it will go in the other half space, the magnetic field there down will return the electron along the line, and so on. So you have a kind of, you can even show in the Hamiltonian that this is equivalent to a parabolic or quantum well approximately. So you have the electron trajectory bound along a line which corresponds to the vanishing magnetic field. This is called snaking orbit, and it's also something very common in the magnetic lenses, in the old TV tubes. And this is, let's say, a mechanism for a lateral localization of the electrons. What is the consequence of this kind of states? So if we look at the energy spectrum now on an infinite wire, without magnetic field, we would expect some sort of parabolas corresponding to, with a momentum corresponding to the free motion along the length. Something like this. Now if the magnetic field is strong, then we can think about two cases. If the electron is on the sides, then it will travel along these snaking orbits approximately like a free particle, something with the energy dispersion approximately k squared. But the electron can also be here if it will have enough energy. But to be here, the electron has to rotate, like on very small cyclotron orbits. The energy of a cyclotron orbit increases with the magnetic field, proportional to the magnetic field, like Landau levels. So these states would correspond to some sort of local Landau states. These states would correspond to propagation along the snaking orbits. And then this means that if you increase the magnetic field, the Landau orbits will increase, but the snaking states will increase less, because they more or less experience a zero magnetic field. Increase the magnetic field, they are more and more pronounced there, but pretty much at the same energy compared to the states on the top and on the bottom of the cylinder. This means that at high magnetic fields you have a separation of these energies. This means that the density will actually become non-uniform. So if you have a magnetic field strong enough, then the electrons are going to travel, if you have sufficiently few electrons, otherwise the whole spectrum is full, they will travel on the sides. And these type of states were indeed known also before we started our own calculations. But the question which was not answered: how are these states going to behave in such a way that they can be observed? Or will they be observable, or they will be washed out in the whole energy spectrum? So we did transport calculations based on the method that I was describing, with very weak coupling to contacts. And we consider the contacts also limited around the circumference. And we found that indeed, because at strong magnetic field, the snaking states tend to be ground states, they can be seen as resonances, isolated peaks in the conductance. So our prediction is that for parameters which are realistic, although strong magnetic field and nanowires of the known size, one should be able to see the snaking states as peaks at low energies. This is the energy spectrum corresponding to a nanowire, I think 30 nanometers in diameter and about 100, 150 in length. And then at large magnetic fields, you see the snaking states, whereas the cyclotron states tend to grow linearly with the magnetic field. And now you can see the wave functions for the snaking states. So now if you, here it's the surface, it's the open surface, so this is 0, this is 2 pi. So if you take the cylinder, make it flat, and here you have half pi, and here you have 3/2 pi. So these are the sides. So you see the localization probability. And what we predict is that if you would have an electric field, then you would see peaks splitting, because the snaking states are in fact degenerate. So for the infinite case, you have one propagating ahead, like I'm looking to the bottle, and one propagating back. So of course, if you look, these are always symmetric spectra. On the finite cylinder, this is in fact not true. So there is a very small splitting of the two states, because of course now we have finite boundaries of the boundary conditions and so on. And if the symmetry of the cylinder is broken, then we should be able to see we split. These are again our prediction, and of course, because usually the contacts, in the way the experimentalists are placing them, or gates, they do not surround the whole nanowire, then depending on the orientation of the magnetic field or relative orientation, then the snaking states can come closer or underneath the contacts or not. So then we would have a different magnitude of the peaks depending on the orientation of the magnetic field relatively to the contacts. Now, in recent experimental results, another what we believe is another effect of, or a related effect due to the snaking orbits. In the experiments done recently at Jülich by Sebastian Head and Thomas Scheppers, they have, as I showed before, a nanowire with several gates, and when they put a voltage on two of them, they put voltage on two at a time in such a way that they can create potential barriers at different distances. So 100 nanometer distance if they activate gates 5 and 3, 300 nanometer distance if they activate gates 5 and 2. And they see oscillations of the conductance which scale in frequency with the distance between the gates. So to do such a calculation, we have to use a method where we can use contacts which can be variable, which can be more transparent than the simple tunneling contacts. Because with the tunneling contacts, we can only pick the density of states. So to extend our calculations, we used a scattering method which is based on the R matrix. And it is also another standard method in this field. There are very many versions of the scattering method. So very briefly, the R matrix method consists in defining a scattering area and calculating in the scattering area the eigenstates of the Hamiltonian, but not with vanishing boundary conditions as it is done usually for closed systems, but with boundary conditions that correspond to vanishing derivatives. So not with Dirichlet, but with Neumann. Once you have these states with Neumann boundary conditions, then you have to describe the wave function in a basis corresponding to these eigenstates and make continuity of the wave function with the states that exist in the leads, presumably plane waves. So in the continuity equation, you can pick the S matrix, which depends on another matrix which is called the R matrix, which contains the Neumann boundary conditions. So then you have the transmission function and the conductance. Again, I do not want to insist. We can discuss the method separately. Now, the first approximation and the simplest approximation is to consider a nanowire in the presence of the magnetic field, but here in the contacts to neglect the magnetic field. So by doing this, we have two advantages. One advantage is that we have a simple treatment, because of course including the magnetic field in the leads is another problem, and sometimes you want to avoid that, because physically the leads have a completely different physics than the nanowire, which is semiconductor. The leads might be metallic and whatever. Of course, rigorously speaking, you don't want to do that, but in a first approximation, this is, I would say, a first choice. The second advantage is that, in fact, you can create a magnetic barrier. So if you have a magnetic barrier, then you would have reflections, transmission and reflection. And now, the energy spectrum, which is obtained with the Neumann boundary conditions, which is called Wigner-Eisenbach, has this structure. Remember the energy spectrum obtained for the finite nanowire. energy versus magnetic field. So here we see the snaking states becoming the ground states, or low energy states. Here we see an additional feature, this braiding. It tells you that the snaking states, which are always in pairs, in this example, in the closed nanowires, here they make some sort of interference. If we attach potential barriers at the ends of the nanowire in such a way that we reduce the coupling and have a weak contact, we indeed obtain the same results as for the isolated nanowire. Now, the interpretation is that there are snaking states traveling, so there is another one on the other side. Let's say, or maybe I have another color. And now we have a kind of closed loop. So one state goes on a side and returns to the other side. And it returns because it's reflected by the barrier, be it magnetic or potential barrier if it is not too strong, too high. Because if it is too high, then there will be a reflection only for. You can't actually make the snaking states to talk to each other. And we get some oscillations which show in the versus magnetic field a period in magnetic field which corresponds to the flux quanta, where the flux is the magnetic field divided by the projected area, so the length divided times 2 radius. And this is with a magnetic barrier. Now, to go further and try to create a model which is even closer to the experimental model, we took a long nanowire, so 2000 nanometer, and put barriers in the middle. Now, increasing the length of the nanowire, the magnetic barrier, which is still present, is actually having a less and less influence, because the oscillations would scale with the length and they would vanish. But now, with the potentials, we would have oscillations approximately corresponding to the length between the barriers. Whereas without the potential barriers, we get some steps in the conductance versus magnetic field. So all these steps will be with very, very, very small oscillations because of the magnetic barriers, but then the effect is very, very small. So this is what we think it explains the experimental results, that the period of the oscillations becomes smaller when the length, distance between the barriers, we can call them quantum point contacts if you want, is increasing. And the paper is now submitted, the experimental paper. Now I will talk about the third type of localization in the corners. Remember, the cross-section of a nanowire typically is a hexagon. It reflects the crystal structure. In some cases, they can also do the circular nanowires. But in other cases, they can do square nanowires or triangular nanowires, like in this example. Now, what is interesting about the corners is that they localize states. An older story about bent nanowires says that there will be bound states at the corner of just an ordinary nanowire, or if you want to have two nanowires making an angular junction. In the polygonal geometry, we started solving the Schrödinger equation on a grid. So originally it was a polar grid, and then we restrict to the sites within the polygon. And then the states with the lowest energy, they have probability maxima in the corners. And there is a group of states, as many as corners, times 2 because of the spin. And then they are, so the spin is not included here, 6. So these are the corner states of the hexagon. And then the states with higher energies tend to be localized on the sides and have minima on the corners. Now, if we do the same calculations on other polygons, triangles and squares, the corner states are even better separated from the side states in energy. For example, for a nano ring, let's say this is a triangular ring of let's say from the center to the corner, we call it radius, because you can put a circle and that will be 25 nanometer and the side thickness 5 nanometer. Then we have something like 120 MeV between the corner states and the side states. If you have a larger, then you can have 60, 50. This is a energy separation that is huge compared to the energy spaces which you have in a circular ring, which are typically milli-electron volt. And then for the square, we also have a considerable gap. So you see 1, 2, 3, 4, 5, 6, 7, 8 states corresponding to the corners. 4 corners, 2 speeds. And the hexagon has a more modest gap. So it is tempting to look at the triangular core shell as candidates for a very strong corner localization, of course depending on the aspect ratio. What is interesting, for example, the electromagnetic absorption. Electromagnetic absorption can occur within the group of corner states, but which have a very little dispersion. Or maybe I should say the interesting aspect is that the corner states tend to become a degenerate group. But still, depending on the aspect ratio, you can see a transition or an optical effect of transitions between corner states only, but you can see transitions in a completely different domain between corner and side states. So one would be some terahertz, the other one can be almost or far infrared, if not even, probably not visible, but some infrared. So with these various calculations in the simplest approximation for the electromagnetic absorption, and indeed given some selection rules. So here we have density of states. Here we have absorption lines corresponding to clockwise or counterclockwise light polarization. So there is a small shift because of the behavior of the energy spectrum in the presence of a magnetic field. Of course, you can have polygons which are not symmetrical. And in that case, the sharpest corner will create the lowest energy state. So you can have these funny states with a very little difference in energy between them. It only depends on either the sharpness of the corner, or, like in this case, about a small, they depend on a small difference between the sides. You can have an electric field actually which breaks the symmetry. Then we did a study of the localization of the corner states and of the side states with variable aspect ratio, getting the same radius and increasing the thickness. So you can see the evolution of the corner states when the thickness increases 3 times, and here the side states. And then you see that side states actually start at some point populating the corners if the thickness increases. The energy of the corner states and of the side states depends somehow differently on the thickness. The corner states, the energies of the corner states depend on the area of the corner, and then if you look at the side, you see a different shape. It's not so easy to explain or to understand, but the net effect is that although all states will decrease with increasing the thickness, but then the gaps do not increase, do not decrease monotonously. So you have the gap between the corner states and side states with a minimum at for this example, at around 16 nanometer thickness. So, to summarize, I would like to say that there are complex phenomena that can occur in this geometry. Although looks simple, the geometry, then the situations can be quite complicated. And I described Aharonov-Bohm-like oscillations of the conductance with the axial magnetic field, another kind of Aharonov-Bohm oscillations with the transverse magnetic field, and corner localization. And there are other things that we are working on. The effect of snaking states on the thermoelectric transport. Then we are working on Coulomb interaction in the corner states and on the side states. And then we are looking at Majorana states at the corners, which would become kind of edges. And we have in Iceland a new funded project called core shell nanoantennas, where we would like to calculate collective states, plasmons, and electromagnetic absorption, electromagnetic radiation. And this is team that hopefully I did not forget anybody, and I would hope to increase the list. It's Anja Sitek, who is postdoc in Iceland, and she is moving now this summer from University of Iceland, which is the largest university, to my university, which is Reykjavik University, which is just across an airport. And Thomas Ordrosdal was a master student and did a great job with the calculations of the oscillations, Aharonov-Bohm on the snaking states. Vidar Gudmundsson, my sort of lifetime collaborator. Siggy Erlingsson and Gunnar Thorgilsson and Kristin Torfason from my university. Lawrence, who is in this room. And the experimental collaborators, our friends Thomas Shepers and Sebastian Heck, who is finalizing his PhD thesis from Zurich. Hopefully, I would add more people. And finally, this is me. I'm not sure if you can observe, but I'm testing, I'm doing observation, experimental observation of Coulomb effects. Microwires, not nanowires, but anyway. So I'm not sure the contrast allows you to see that I have hair. I mean, what we changed is the coupling. Yes, it can be done with green functions, but we did it differently. Actually, Siggy has a method based on the non-equilibrium Green's functions, but he had it on a flat wire, and only a couple of months ago he could find time and roll the flat system, and yes, he gets the same results. So it's only a matter of how we evolved. On the other hand, with the R matrix, we still have this energy spectrum to contemplate and to try to correlate with it. Although this is not an energy spectrum that we are used to. We are used to the energy spectrum in a finite system and a closed system. This is an open system, so you cannot put too much physical interpretation on this. But still, because its oscillations are visible in the spectrum, at least for the magnetic case, because for the electric case, or for potential barriers would be more complicated. The longer the wire, the denser it becomes. So then we can say that the oscillations, in fact, are a replica of the spectrum.
I didn't quite understand in this calculation the discrete spectrum you obtain with the 4 Neumann boundary condition. If I understood well, you have the open nanowire, but boundary condition is not
no, you
vanishing wave function, but vanishing derivative.
Exactly. So this is a finite length, L. What we are used to do is to calculate the energy spectra when this function
vanishes at the boundary.
Yeah. So this is the equation that we usually solve. But you can also solve with the condition that the derivative. So in other words, very simple.
This gives you a discrete spectrum?
No, instead of using sinuses for the longitudinal basis, you put cosines. That's all.
But it's discrete, no? You have a discrete set
Yes,
of
you have a discrete spectrum. I mean, you call it open, but open is formally only because you have the Neumann boundary conditions. So you have another spectrum. In many cases, it looks similar, or okay, but what you have to be careful with is those terms of the Hamiltonian that depend on the linear. They are linear in the momentum, because they would be Hermitian only with this condition. Then you have to make them Hermitian and Yeah, yeah, and there is a small technical aspect.
Is there any other experience again?
Do you want to give explanation for this border localization? Because maybe speaking, I would think that electrons would prefer to have a low kinetic energy. So they would somehow prefer to be extended, to just lower the kinetic energy. But how do you find that these corner states have low energy? Because interaction with the confined material?
One analog is a bent wire. So if you admit that the bent wire would in fact create an effective potential well, then it's the same mechanism.
You have a closed one.
Now, yes, you have a closed wire. So for the closed wire, let's say if you have a circle, you have the energies proportional to m squared. So the lowest energy would have, let's not talk about speed. So the lowest energy corresponding to n equals 0, or the energy spectrum will be sort of, okay, at least the lowest states, right? Now, these states, low energy states, would correspond to the smallest kinetic energy. And now, if you think about n equals 0, this has no kinetic energy. So the state that you would think the lowest, and then if you have corners, it won't rotate, so it has to go in the corners.
The side states have more.
It is now, as a sort of interpretation, if you have the three states, you have three corners. You can think about a sort of degenerate, so in each corner will the state go, in all three. But if you think about the basis in the real states, then you can think about the corners as part of the basis. So you need to fill three corners independently. So in this sense, the number of corners gives you the number of low energy states. And again, what I find very interesting is that they are separated energetically quite a lot from the side states, depending on the angle. What's the effect of spin and the effect of the spin? To a first approximation, you double each of these states. So, to a first approximation. Then, what we are looking at now is that if you have Coulomb interaction, then there are other situations, because you can have in corners two electrons, but only they have opposite spins. So then it's a different aspect.
If there are no more questions, let's thank Andrei again.